All right, so I wanted to go ahead and actually take a look at the paper 2 style questions on this thermal physics practice test. So looking at the first problem, it says, let's just be really clear. I notice there's this DC power supply, a bunch of weird symbols here. And of course we're going to be discussing these next semester. However, I want to get really clear on just one small thing, which is that we have this water heater, we have some water, some other things. Let's just kind of get clear. This is the thing that matters. We've got something transferring heat into water, and basically we're going to be steadily boiling water away. So let's just keep things relatively simple and just say the following. So we have this water, this heater, and we're told that the change in the reading of the top pan balance is taken during each 200-second interval and calculated, and an average is found. And we can actually get the power of the heater, again, using the same formula we used for number 3 in the previous test. I'm not going to do any kind of problem on your real test where you would have to take the electrical power as I times V, but I'm just going to write that formula down here so we can use it. Now, the next idea is we're looking at the change in the reading of the top pan balance, so the mass, and we can just kind of see the power of the heater multiplying together readings and just kind of see what's going on. So it says, suggest how the students would know when the water was boiling steadily. There's a couple ways that we can do this. First, we would need to know that the water is escaping at a steady rate. Okay. Since Q is ml is the equation for boiling, steady power means that the heat escaping with respect to time would need to be steady. So we would need to see just a steady mass of water evaporating, indicating a steady absorption of heat and power. Okay. Next, it says, explain why a reading of the mass loss in the first 200 seconds and then a mass reading in the next 200 seconds would be taken rather than one single reading of the mass. By having time intervals, we can track if the mass loss is steady. Because if we track it this way, it should be equal. And notice I'm kind of formulating my answer using my own words here, just because I want to be really clear. Sorry, I'm just going to make sure that I loss. There we go. Just wanted to make sure that I'm kind of writing this in my own way, in a way that's actually sort of legible. And just kind of want to write that word loss much more clearly than I have it here. L S T. There we go. But the answer that I've written here should completely match the answers in the answer key. So the student repeated the experiment for different power supplied to the heater. We've got a graph, and we want to just plot. And we're told, okay, let's graph the line, which I did here using a ruler. And we want the gradient of the line as drawn. So this is power versus mass. And let's just be clear. If we want to get the gradient of this line, I'll choose this point here and this point here. So this looks like just a little bit below. So I would say this is about 1.5, comma 48. And this is 5, comma 90. So let's get the gradient. And that gradient is going to equal 90 minus 48 over 5 minus 1.5. And when we actually get that gradient, I'll just do that right now. So that's going to get me, whoops. Whoops, sorry. That's going to get me a gradient of 12. And, sorry, I had to pause for a second. Let me also get the units on this. So the units on this will be watts per gram, or watts gram to the negative 1. Now, let's just be clear here. We know that the power P equals ml, and we'll need to use the gradient of the graph to determine a value for the specific latent heat of vaporization for the water. So let's be clear here. First, this is power, this is mass, and what we know is that the mass of water evaporated per second is 200 grams. So what we have here is basically the case that the gradient is not our latent heat of vaporization. It's going to actually end up being that we've got L over 200 as our gradient, because the gradient here is in fact related to, we need the power part there, and then the other thing is, I'm sorry, that's not 200, that's 200 seconds in a gram, so this is L over 200, it's a time thing. So I need to take 200 times 12, and that's going to end up getting me 2,400 as, and that'll be joules grams to the negative 1. Here, if we have 0 grams, we should have 0 heat, so we should really have an intersection of 0. Clearly, this is some kind of systematic error. Because the gradient's correct, or the gradient makes sense. Sorry, so it's systematic error. Because our gradient makes sense. Okay, so there we go. In other words, we got the right answer, but everything's off by a certain factor, which is what a systematic error is. Now here, what do we mean by an ideal gas? Let's keep this really simple. An ideal gas, okay, we got a bunch of criteria. Keep your life simple. It obeys Pivnert. we actually have what are called non-ideal gases. And if you stay in this business and you go to engineering school or you become a chemical engineer, you'll get to study all about those, and it's exciting. So now here, check it out. We've got a volume, 20 megapascals. That's 20 times 10 to the 6th. And then let's be really clear here. We are told that we have something at 17 degrees. Let's convert that to Kelvin. So that's 290. Let's get the number of moles. So PV equals nRT. 20 times 10 to the 6th, that's what the mega means, equals times V, which is 2 times 10 to the negative 2 equals N times 8.31 times T, which is 290. And when we isolate N, we're going to end up getting about, now if we're going to do sig figs, I'd say 170. Really, it's 166 when we do the math. Now, the number of atoms, you're going to take 170 times 6.02 times 10 to the 23rd. And that's going to give us about 1.0, whoops, times 10 to the 26th. So that's good for questions 1 and 2. And we'll do questions 3 and 4 in the next video.